Hello, everyone. Good morning and welcome to MACSMIN 2024. Today we start with the talk by my postdoc Yury Elkin on the EPSRC New Horizons grant, and Yury will talk about complete and continuous invariants of molecular graphs. Over to you, Yury, please.
Yeah. So hello, I'm Yury from University of Liverpool, and I'm holding a talk about complete and continuous invariants of molecular graphs, as Vitaly mentioned. So we go to the first slide, and so we have this object called molecular graph. So basically, when we're looking at molecule, we're looking at an Euclidean graph in our tree. So the points that are the atoms. So the atoms are the points in the graph, and the edges are formed by their bonds connections. And in our case, when we are modeling this structure, we don't care about what kind of edge there is and about type of molecule, at least at this stage. So basically, we're looking only on the abstract graphs that are located in Euclidean space. And then we want to figure out when those graphs are similar. And for this, we need this thing called equivalence relation. And so basically, relation can be anything, but equivalence relation is a relation that has those three properties. So two objects, well, there's like this reflexivity that if that object is always related to itself, and then there's a symmetry that if object is related to, if object A is related to object B, B is related to object A, and then there's transitivity that if A is related to B, B is related to C, then A is related to C, and those three conditions guarantee that that when we have this large set of objects, then we can put them into disjoint classes, and those classes don't overlap. So we have a large number of objects, and then they go into classes, and those three axioms guarantee that. And yeah, then we want to figure out, are two molecules the same or not? And well, basically, if we will look just at the chemical composition, then there will be a problem because there are like two different molecules that have exactly the same composition, but their geometry is different. So as we see two examples here, where we have like two chlor, two of those hydrogens, and because of their different positioning, those two molecules don't equal each other. This is why we kind of need to look at the geometry. And yeah, there are obviously other properties, but even if they share some kind of one property, it doesn't mean that they're the same. And we're looking at the equivalence, geometric equivalence. So we have a molecular geometric structure, and we want to kind of have equivalence by the rigid motion. So if we have one geometrical shape and other geometrical shape, we want them to be the same, even if we move them around, rotate them, and do things like this. And we are looking at the kind of equivalence by the rigid motion, and it's geometrical one. And so we call those descriptors. So any graph, its isometric class can consist of infinitely many graphs, and now we define an invariant. So invariant is a function from graphs that are located in the Euclidean space in our case to something simpler, like a number of vectors or numbers or whatever. And basically, the invariant has the property that if G and F are the same, then the invariant shall be the same. And obviously, if the invariants are not the same, then those objects are not the same. So this is kind of, at this stage, this is just a property or descriptor. And yeah, for example, one of such descriptors could be center of the mass. So if we just have some kind of point cloud and another point cloud, then we can look at the center of the mass. So if they're the same, then the center of the mass shall be like at the same point. If it's not, then, well, assuming that they're not centered. Okay, so but then we get to this complete invariant. So obviously there can be many descriptors, but they don't classify the object. So to make the classification, we need this concept of complete invariant. So basically, we want that if two graphs G and F are not isometric, then their invariant will be different. Or if the invariant is the same, then we can conclude that two of the graphs are exactly the same. So there's this example called DNA that identifies a human. So a function from human to DNA is the same person, but actually in practice, I don't think that it exactly works like this, but almost. So
Yury,
yeah.
if you could stop on that slide, since we run our meetings and talks informally, so feel free to ask questions at any time, especially if your background is different from mathematics, because we understand we introduce already technical concepts. So feel free to ask questions, okay? And yeah, Yury, feel free to encourage questions on your side. Thank you.
All right. So, Vidal, you had no question for this slide. Right. Yeah. So we have this isometry problem for graphs. So we want to design invariant such that is a map from isometric classes of graphs to a simpler space that satisfies this. The first property is completeness, that if A and B are isometric, if and only if the invariant is the same. So it's kind of one-to-one mapping. And then we want also this invariant to work in a Lipschitz continuous way. So basically that if there is, in some sense, small change in the graph, then it will correlate to a small change in this simpler space. That it does kind of this transformation in a smooth way. And then there's some more practical conditions. So we want this completeness that actually like any that we can reconstruct any graph from this invariant. So so that we have this large set of graphs and they all map to some this simpler space. And then we want it to be invertible in the sense that we can go from this invariant space to this or get some representative of the graphs, because like there are many graphs that can have that are the same but the rigid motion, but we want to have like one representative from this class, and we want to go from this invariant back to one representative. And then also, of course, because this is a practical task, we want it to be computable. So for fixed dimension n, the invariant, the metric, and reconstruction should be computable in polynomial time, so that we can actually do something with this. And then we have this comparison between graphs and atomic clouds, is that obviously in atomic clouds, the task is a little bit more easier, because in atomic clouds, we just have a point cloud, but in graphs, we have this additional edge relation. And obviously, this task becomes much harder because we have, like, if we list all the possible connections, then there are 2 to the power of and all the pairs, so like n over 2. And so the number of theoretical combinations is much larger for the graphs. But in practice, because we're looking at the molecules, obviously there are like less of possible connections. So they're like in theoretical sense, yeah, this is much harder problem, but in practical sense, it's not necessarily that much harder. And obviously, we use this project for classification and to find duplication in this QM9 database that consists of 3D molecules. So there was this QM9 database that had around 100, so 130,000 K molecular graphs, and and we actually did some classification and the process of finding duplication for this. And let's go to, so to do this task, because obviously there's a large number of molecules, we want them. And if we look at all the possible pairs, it's a large number. So if we multiply 100K by 100K, the number of combination is really large. So to actually produce a classification, we need to start with some simpler invariants to actually to be able to understand which of the pairs are close. So we start kind of with this simplest invariant. So we have a point cloud for the vertex set of a graph. Then first we use translation to, we actually don't need to use translation. We just find center of the mass, or use translation to get the center of mass to 0, and then we compute the distance from every vertex to 0, and then just place those distances into some vector and sort the vector. And this is one of the easy invariant, and it's computable linear time, and its advantage. So so already using this SRV invariant, we can see that so this is SRV1 was the distance from origin to the molecule that is furthest away, and SRV2 was the second furthest molecule. And then we had some property G in this and from this graph we see that actually this invariant already, or the first two kind of numbers of this invariant already classifies or gives some idea of those atoms, that we see that if two of the kind of molecules are nearby by this invariant, then the properties are also close, and we get this nice graph.
Yury, since this is the first geographic style map of a real database, could we discuss a bit more details of this plot? For example, could you repeat again what one single point, what does one single point represent in this scatter plot?
So every single point here is a molecule in the QM9 database.
And the coordinates?
The coordinates, so the first x coordinate is SRV1. So we had this in previous slide. I introduced this sorted radial vector that, and basically this SRV1 means that it's a distance from origin or from the center of the mass of the molecule to the furthest away atom in the molecule, and SRV2 is like the second furthest away. So basically in x coordinate we have SRV1, and in y coordinate we have SRV1 minus SRV2.
Yes, so on the y-axis we have a difference, and for example, when this difference is 0, what does it mean geometrically? We have here many points on the horizontal axis. So,
Yeah.
so in these molecules on the horizontal axis, what geometry restriction do they have?
Oh, you mean like by the y-axis?
Yeah, the horizontal x-axis.
Oh, so like this.
Yeah, when the difference is 0.
I mean that at least if this is 0, then we know that SRV1 is SRV2 is if you look just at like this line.
So there is at least some little symmetry. So it means that two distances from the center of mass to two most distant atoms are the same. And for simple molecules, and well, this QM9 database contains all simple molecules you know. For example, well, the water molecule is also here. And well, an interesting question is to guess where exactly the water molecules consisting of only 3 atoms is located in this sort of a waterfall image. Any suggestions where do you think the water molecule is on that plot? Yeah, actually, to help you, I have a water molecule with me. So it's 3 atoms only, as you can guess, H2O, so 2 hydrogens, 1 oxygen, right? And geometrically, it is, well, a triangle, right? So only 3 atoms, but not an arbitrary triangle. It's, so what can we say about this triangle? So anything interesting?
It's equilateral.
Well, it might look equilateral, but not exactly, because 3 atoms are not the same. If we had 3 atoms, then it might be possible indeed to have an equilateral triangle in principle. But for the water molecule, this triangle is isosceles. Right? So it's symmetric, right? So one.
Oh, yeah, that's what I meant. That is what I meant. I just meant 2 sides of the same.
Okay. Yes, isosceles triangle. But also, so in this isosceles triangle, for example, can you guess from the center of mass to 2 most distant atoms, these distances will be the same or different? The same, exactly, because this is a simple molecule isosceles triangle, right? And so where does this water molecule in that plot? Yes, at the bottom. And so there are actually many molecules like that at the bottom, as you can imagine. So there are many simple molecules that are isosceles triangles. Actually, one more is carbon dioxide. So it's also isosceles triangle, but different, right? So they're rigidly different. So the water molecule is yeah, a bit special, as you noticed this morning. So the water is abundant, but also it's a small molecule, right? So any guess where this molecule, a small molecule on in that plot? Again, Alison. Yeah, exactly. So you have already noticed that all our coordinates here measured in angstroms, right? So we measure distances between atoms like in angstroms, and when distances are small as for that very simple small molecule, then of course it's simply number 1 molecule on the plot at the bottom edge. Any more questions about this particular plot?
Is the property here the color?
Color. Yury, could you explain again the color?
So it was this G property. Do you remember what the G property was?
Okay, so QM9, this is a database with 3-dimensional geometry, and this geometry was obtained, so atomic coordinates were obtained through optimization of various functions, in particular energy. So for every molecule in QM9, we have, I think, 14 different properties obtained computationally, and G, so-called free energy, is one of them. So here we highlighted well, every molecule by color, well, by the values of this G energy. but in principle, you could use another property. Yeah. Any more questions? Okay, then, yeah, Yury, feel free to continue.
All right. So
Can I ask a question?
yeah.
Marjan, please.
These molecules that you have in this diagram, all of them have 3 edges, or what is the maximum edges?
Maximum edges of a molecule.
Yes.
Okay, so I'm not sure about maximum edges, but I think maximum number of atoms is around 30.
29, if I remember correctly, but it's called QM9 because it contains up to 9 non-hydrogen heavy atoms. But including hydrogens, it's up to 29 atoms. Yeah, we are not sure exactly about the number of edges. Yeah, obviously more than 29. Probably, yeah, several dozens.
Thanks.
All right, so and yeah, in this picture, this contains all QM9 molecules, and then we have a similar one, so SRV2 and SRV2 minus SRV3 and property G here, so looks similar. And then we have another invariant that is a little bit more harder to compute, is the sorted distance vector. So so basically we list all the interpoint distances. So for example, in this graph, we just kind of list all of those, and then we get, yeah, like M combination 2, or yeah, so M choose 2 interpoint distances, and then we put them all in the decreasing order, and yeah, and that forms an invariant. And so SDV is in practically a strong invariant because well, it could distinguish almost all clouds, except some singular examples. So and then we compare SRV to SDV. So while SRV has M ordered distances, the SDV has quadratic number of those, and so basically while SRV is can be computed linear time, then the SDV is computed in this quadratic time. And yeah, let's go to the next one. So in this we have another invariant that is in some sense stronger. It's called PDD, or point distance distribution. Is that we have those points, and basically for every point we list its distances to all the other points in decreasing order, or in this case I think increasing order, and place them into a row of a matrix. So this row corresponds to we actually place them as rows, and then we collapse. So there are 4 vertices here. So originally this matrix looked like had 4 rows, but then because of the symmetries, we collapsed 2 rows into the same and put coefficient half instead of coefficient 1 of the 4th. And this actually forms invariant as well. And this is kind of it takes the same amount of space as the this SDV, but because it's ordered by kind of the points, it's more precise. And those matrices can be compared by the Earth mover distance, which is and basically we want to find a way to kind of or find the distance between those 2 matrices, and how we can collapse one into another. And one of the good thing is that it's continuous, but obviously it's much slower to compute this than just L infinity distance between two vectors. And then even stronger invariant will be the pairs of distances. So for every base point, we basically compute its distance to all the other points and also to the origin. So for base point, oh no, actually we have like base point, then we have origin, and then for every other point, we compute this distance to this base point and origin, and we get a set of those pairs, and we can put them into a vector that kind of will have unordered columns, and it forms this kind of 2 by m-1 matrix. And then and then this can be generalized to a nested base distribution. So we will have a pair of the base points and also those unordered columns as the C matrix. And to encode the edges, we can assign in such a way that in all the computations, if there is an edge, then we put a plus sign, and if there's no edge, then we multiply by -1 every distance. And so, yeah. Let's see if there's, yeah, so in this case, we just had a base point and an origin, and this actually formed the nested base distribution, but this can be generalized to a thing where we have many base points. So we can fix multiple base points, and then obviously we can compute for any other vertex, we can compute a distance to origin and all the other points. And because there is this many points, we can it actually transforms into kind of a nested distribution. So so basically, if we have just 2 points, h is 2, then in this kind of outer layer, or yeah, we start with the 1 point and then we choose another point, and so you can think of it as a pyramid in the sense. And then when we have those combinations of like 2 points and all the other points, distance to them, and also go over the combinations we get. So I think it's hard to explain it in this slide, but it's basically a harder invariant than the other one. And so actually, probably this graph at least helps to understand the general idea. So this NBDG is our new invariant that we defined in this paper, and there's a variant that states it's complete, it's like Lipschitz continuous, it's computable in polynomial time, and so on. And so here is a graph about the kind of the complexity or hardness of the invariant or its precision as well. So we have SDV, that is like that simply contained the vector of all the pairwise distances in the single vector. PDD contained them, but kind of in a matrix shape, and NBD contained kind of what PDD had, but also distance to the origin. And basically, this NBDGH was a generalization of this when we can have pairs or multiple parameters. And there's a graph illustrating them, their relations. And so so basically, yeah, here's basically the same thing. So if we want fast invariant, then we can use SRV, that is simply linear. Even larger invariant will be SDV, PDD is obviously stronger, and then NBD is also quadratic and a bit stronger than PDD, but basically uses the same information. And then if you want a complete invariant that that has a complete classification, then we can use this NBDH in such a way that this parameter h corresponds to the dimension of the point cloud. And if we add the sign, then it can classify all the graphs. And all the invariants are Lipschitz continuous. Or the metrics of the invariants are Lipschitz continuous. And so what we did is that we had this QM9 database of 100,000 K plus molecules, and basically this corresponds to to this large number of pairs. And so we started with the like this large number of SRVs, then compute or the pairs. We computed the L infinity distance between all the SRVs or all the pairs of SRVs. Then we went to SDV, where we took like 1% of this number and computed the SDVs on those pairs, and then again took the 1% closest pairs and computed the PDD pairs. And then we continued with our more sophisticated invariants to compute like 10,000 for the last one. And the whole process, it took only a few hours on the computer. And to summarize this, so we know that the molecules can be distinguished purely geometrically, because like the closest one that has like different composition is like 0.014, but our invariants can recognize that, or even like closer ones. So basically, we are able to completely classify the molecules just using the geometry and find the point cloud of the graph structure. And actually here I have some pictures related to actually, maybe I should like zoom this out. Let me see. Or no. Yeah, so okay, I can just say, well, so on the bottom we have like the SRV invariant, the easiest one. Here we have SDV, and here we have the just similarity graph. So for the 3,000 closest pairs of QM9 database sorted by this hardest invariant, we kind of compare those. And if you look at the scale, then I think the like L infinity SDV and the SRV will be the same if they will be like at this line about, I think, and they're pretty close. Then similarly we have SDV compared to PDD. So on the bottom we have SDV, and here we have PDD, and again I think the linear line would go here, and we have this PDD compared to this NBD G1. So I think again, so we look at this scale, then at least the first ones are close to each other, and then this is kind of surprising that NBG1 and NBG2, when we kind of add one more parameter, then really it doesn't help us that much. So they're really close most of the time. I think, yeah, so this summarizes it. So yeah, I don't have anything else.
Thank you, Yury. Thank you for your presentation. Let us thank Yury, please. Okay, so thank you for leaving time for questions. Let me first stop the recording.